Alright, y'all, so we're hitting 2 sections in this video, so hold on, it's gonna be great. But you're gonna do some proofs in your groups during class, so that'll be really exciting. So we're looking at the integral test and then some comparison tests, the direct comparison test and the limit comparison test. And these the crux of these is on boundedness and thinking about like monotonicity and those kinds of things, because those really help us have more of a clear picture of what's going to happen to another function that we don't know about. So integral test, we're looking at improper integrals, and then comparison test, we're going to look at limits, and we're also going to look at just directly comparing with 2 different series. So let's get to it. Our integral test is if we have a positive and continuous and decreasing function, function f, for like starting from 1, which is our first positive integer, and going on from there, and we can also describe our series, our sequence, the terms of our sequence that we're adding up in our infinite series as matching our function. Then we can tell things about our series and our improper integral. They're either going to both converge or they're both going to diverge, because we're either going to have a number or we're not going to have a number. So converging means that we have a number, and diverging means we don't, that our limit does not exist. So you are going to prove this with your group, but let's look at these pictures where we have our function. Suppose it's, this decreasing positive function that matches our a sub 1, a sub 2, a sub 3 there. And it also there, we can look at those, we can look at this integral as the area underneath the curve, right? And we can think about that area in 2 different ways. We can think about either circumscribed, which means that we're looking at the upper sum, or we're looking at inscribed rectangles, looking at the lower sum. And for this, the circumscribed rectangles, that's going to be the left Riemann sum, and the inscribed rectangles is going to be to the right Riemann sum. And the left and right, when we have a limit for those and it matches, then we have a definite, we have an area under our curve, so we have our integral. So there's your connection between our series, our infinite series, and our improper integral. So we're told to use the integral test, so we're going to take this and we're going to make it into a function. And so this is going to be our function x over x squared plus 1. And this we can do a u sub on, with u is x squared plus 1. So then du is going to be 2x dx. You might be able to do this in your head at this point. That's awesome. So if we're looking at our improper integral of x over x squared plus 1 with respect to x, this is going to give us a limit as b approaches infinity of our integral from 1 to b. And we have, this is x over x squared plus 1, because we're still looking at this in terms of x. And that's going to give us our limit as b approaches infinity. And let's do our u sub, so then we get what? 2, right? 1 squared plus 1, and then b squared plus 1 is still going to be b. And then we're given a 1/2 1 over u du. So that's going to give us limit as b approaches infinity of, we'll factor out that 1/2, and let's look at, this is a natural log of x squared plus 1 from, and that's back in terms of x's, whoops, sorry. But that's okay. So we get, this is 1/2 natural log of x squared plus 1, where we get b is infinity. So we're ending up with infinity minus natural log of 2. So then this, I believe, diverges. So what about this? Well, this, we have a function where we have 1 over x squared plus 1. That looks suspiciously similar to our derivative. We can do arctan, right? So our integral of this is going to be arctan. Oh, we should also just do the check of is this positive and decreasing for x is greater than or equal to 0, greater than or equal to 1? And yes, just thinking about what that function looks like. And so, what do we get? We get integral 1 to b, 1 to infinity, because we don't have the b yet, of 1 over x squared plus 1 dx, and that's going to give us limit as b approaches infinity of the integral from 1 to b of this 1 over x squared plus 1 with respect to x. And what's that going to give us? This is a limit as b approaches infinity of arctan of x from 1 to b. And so what's that? Arctan of infinity. So what's the limit of arctan? Arctan is bounded by positive plus or minus pi over 2. So this is going to be arctan of b limit. B approaches infinity of arctan of b minus arctan of 1. And so what's that going to be? Pi over 2 minus an arctan of 1. So what tangent gives us a 1? Or when on our unit circle do we have a slope of 1 that's at pi over 4? So we got pi over 4. Pi over 2 minus pi over 4 is pi over 4. So we got a number, so this converges. So I guess the our answer is not pi over 4. Our answer is that this series converges. We still don't know what it converges to. All right, here's the direct comparison test. If you know that a sub n terms are less than or equal to b sub n terms, and we're also looking at only positive ones of those, then if the bigger series converges, then the smaller series converges. And if the smaller series diverges, then the bigger series diverges. And like intuitively that makes sense, right? Because if we have a number for like an upper bound, then that means we're going to have a number for our lower bound, because we also have this stipulation that 0 is going to be less than all of our terms. And if we have our smaller one does not give us a number, then our bigger thing is also not a number. So think about how you can prove this with your group, and then we'll look at some of these problems. So just think about, like, are these situations helpful? So pause the video, think about it. Which of these actually give us helpful information? So thinking about our direct comparison test, we're going to keep that in mind. Let me zoom in on this though. If we know for this first one that we have this series is a geometric series, that means that r is going to be 1 over 2, and so since our r is 1 over 2, it's smaller than 1, so we're good to go. This is going to converge. But if we multiply by n for everything, then that is not geometric. But let's think which one is greater. Do we have a case where we have a convergent greater series with this BRB sub n? Is that going to be greater than this one, a sub n? And no, because we're multiplying by n, so our numerator is increasing, whereas in this one, our numerator is not increasing. So we're going to have that this geometric series is less than this other series that we don't know about. So we don't know anything. We just, I don't know, IDK. What about for the second one? Well, we have a P series, and this P series, this converges, right? Because we have P P is 3. And so whenever our P is greater than 1, then we have a convergent series, which is nice. And then looking at this is not a P series, right? This is because we have this plus 1 over here. So let's compare these two series. Which one is greater? Well, the P series is greater because for this one we have this plus 1 in our denominator. So our denominator is going to be greater, which means that our overall value is going to be less. So for each of our terms, our P series is going to be greater than this other term's series, the terms of this other series. So when we have a convergent P series that's greater than this one that's mysterious, then we know that this one converges by the direct comparison test. What about this one? We have, this is easily integrated, right? Because it's, what is that? We can do a U sub, and that's really nice. But this is not easy to integrate. So can we, well, is this helpful? Like, if this is easily integrated, but this series, this sequence, the terms of this sequence are less than the terms of this sequence, right? Because we have an n in our numerator here, but then for b we have an n squared. So, if we know that this converges, then that actually tells us nothing about that. But if we know that this diverges, then we do know that we have a divergent B. So let's see, is this going to be a divergent series? Because if it is, then this is going to diverge. But if it converges, then we don't know what's happening with B. So let's try it. And should we use the integral test? I think so. So we got integral from 1 to infinity of x over x squared plus 3 squared dx. And that's going to give us limit as b approaches infinity of, and then like over on the side, u is going to be x squared plus 3, so then du is going to be 2x dx. And so we have a limit as b approaches infinity of this integral from 1 to b of x over x squared plus 3 quantity squared dx. And what does that give us? Let's sneak this down a little bit. We get this equals limit as b approaches infinity of what? We get, well, this is going to be 1/2, right? 1/2, and then this is going to be u squared in the denominator, so u to the negative 2. So when we integrate that, we're going to get what? Negative, and then u, which is x squared plus 3, to the negative 1 power. And we're going from 1 to b. And so from here, what do we get? We get that this is a limit as b approaches infinity of negative 1/2, and then b squared minus, or plus 3 to the negative 1 minus negative 1/2, 1 squared plus 3 to the negative 1 power. And what happens to this number? We're getting 1/8. Yes? Yeah. Because this part just goes to 0, and then this part down here, that's 1/8. So we got 1/8. So we got that this converges. But that is, since this is a smaller function, right, a sub n is less than b sub n, so then we don't know if that converges or diverges, because the direct comparison test doesn't tell us much. So how are you going to determine the convergence or divergence of this series? Well, what do you want to compare it to? This is going to be 2 plus 3 to the n power. So that's going to be less than, well, all of that is going to be less than our sum from n equals 1 to infinity of 1 over 3 to the n, which is a p series. Sorry, that's a geometric series. That's geometric. And for this geometric series, 1 over 3 is our r, so this converges. So since the bigger sum converges, that means that the smaller one converges by the direct comparison test, which is pretty great. What about the convergence or divergence of this series? Well, we have that this is, we got this 2 plus happening again, so we know that this is less than, I guess we don't need equal to because it's going to be strictly less than, oh my goodness, I can't write sigma. Okay, n is 1 to infinity of 1 over root n. And this 1 over root n, this is a p series, where p is going to be 1/2. The power of n is 1/2. And so this means that this is less than 1, or less than or equal to 1, right? So then by p series, this diverges. So that means that this, the bigger series diverges, so then with the smaller one, we don't know. IDK. Don't know. Oh no. It's okay. Alright, another tool we have in our series tool belt is the limit comparison test. So suppose that you have strictly positive terms in your sequence, sequence A and sequence B, and you get a number as the limit of the ratio of your two terms. And this is a positive number, not infinite. It's a finite number. Then we know that our series A and B either both converge or they both diverge. So think about how you're going to prove that. This is, it's really helpful because then if you can think about a limit, an infinite limit, then, and you know something about one of them, like you know that it either converges or diverges, then you know about the other. And that's super duper helpful. Like thinking back to this one, we could figure this out using the limit comparison test. Because since we know that we have this as a series like A, and then this could be our series B, if you look at your limit as n approaches infinity of our ratio, so we have 1 over root n over 1 over 2 plus root n. What happens here? Well, what happens is that we have limit as n approaches infinity of 2 plus root n over root n, and this is L'Hopitalable because we get the indeterminate form of infinity over infinity. So what do we end up with? We end up with 1. So this is a finite and positive number. Therefore, both of these series diverge. So, the limit comparison test gets us farther than the direct comparison test sometimes. But the direct comparison test is a lot easier to use, right? Because you don't have to evaluate a limit. You just look at your series and compare it and see, does this help? So how could we show that the general harmonic series, so this is our general harmonic series, diverges? Well, we should probably use a limit comparison test. So we know that our sum from n is 1 to infinity of 1 over n diverges. Because this is a p series. So, let's look at a limit as n approaches infinity of 1 over a n plus b over 1 over n. Because we know that if this gives us a finite positive number, then both of these series diverge. So, what do we get? We get this as a limit as n approaches infinity of n over a n plus b. And when we're evaluating this limit, what do we get? We get 1 over a as what our limit gets us to, because we have n to the first power in the numerator and n to the first power in the denominator. So since we have those same things, then just by our infinite limit stuff, we know that our end behavior is going to be the ratio of our coefficients. So 1 here and a there. So the ratio of our coefficients is our end behavior for this limit. So that's our number that we're going to get to. And so since this is positive, right, because we said a is greater than 0, so this is positive and finite. Or we can just say it's like less than infinity. Then the general harmonic series diverges. So take a look at these series, think about what you want to compare them to, and then we'll see what the conclusion is. So like, what do you want to compare this series to? You know, it looks like quadratic kind of, but like what's helpful to compare this to? Something a lot simpler, like just a p-series where we have n squared, right? And so this comparison series converges, and so if you're looking at the limit of the ratios of these terms, then you're going to get a finite positive number, so both of those series converge. What are you going to compare this one to? Probably 1 over root n. Yeah, and that's a p-series also, so that both of these are going to diverge. And then looking at this, what do you want to compare this to? It's like kind of more, seems more complicated. So maybe 1 over n cubed, right? Because if we're looking at, this is like n squared and then 4n to the 5th as our leading, as the degree of our polynomials for our numerator and our denominator functions. Then we can think, well, maybe like 1 over n cubed would be a good comparison. And so what happens to 1 over n cubed? Well, it's p-series, right? So thinking about that, p-series with 3, so that's greater than 1. And so this series converges, and so both of our series converge. So what do we want to do in order to determine the convergence or divergence of this series? What do we want to compare this to? I don't know. Maybe, well, similar to that last one, do we want to compare this maybe to our sum 1 to infinity? It's a really bad infinity, I'm sorry. Of 1 over n to the, so we have a 1/2 power in the numerator and a second power in the denominator. So overall, the degree of our polynomial is going to be 3/2, or our power on n. Sorry, it's not really a polynomial. So what do we have for this series? This is a p-series, and it converges because p is 3/2, and that's greater than 1, and so converges. So let's see if we get a finite positive number as n approaches infinity of our ratio. So you got what? 1 over n to the 3/2 over root n over n squared plus 1. And what's going on there? We're going to get, this is 1, right? If you do just, if you look at the limit, you can do more algebra if you want to, but this is a finite and positive number, so both this comparison and this one converge. I guess I can just converges. All right, let's look at this one. Wow, there is so much going on here. I wonder if we, like, what on earth could we compare this to? Well, actually, isn't like the first tool in our tool bag looking at the nth term test, thinking, does the limit as n approaches infinity of my terms, of my sequence, does this go to 0? Because if it does, then it's possible that it converges. But if it doesn't, then we're adding up numbers that are non-zero infinitely, and so we are getting, we're not going to get a number. We're not going to get convergence. So let's think about that. Limit as n approaches infinity of n times 2 to the n over 4n cubed plus 1. And you might be thinking, L'Hopital, because we have a 2 to the n in the numerator, so that 2 to the n is going to keep on showing up time after time after time. We're just going to be multiplying by ln's of 2's. And we're also going to have a product rule a little bit. And so this is not going to give us 0. And therefore, the series diverges. So some of the things that we talked about, we looked at, well, we just remembered what our nth term test was, which is really helpful. It's generally the first step that you want to make. But we also utilized the limit comparison test, where we're looking at the limit as n approaches infinity of the ratio of two different series, the one that we're given and then something that we come up with. We showed that the general harmonic series diverged. We learned what the limit comparison test was, but we also used the direct comparison test, where if you have an upper bound function, upper bound series, and that converges, then the smaller one converges. If you have the smaller series diverges, that means the bigger one also diverges. We used the integral test, which was looking at improper integrals and infinite series, both either converging or diverging, but those behaviors are going to match, so that's really nice because we can evaluate integrals. And that's about it. All right. We got some more coming, though. There's alternating series. It's very exciting.